Elasticity deals with the deformation in solids, so of a solid. So if we apply a force on a solid, it deforms, even though it deforms extremely little, but there is some deformation. So as an example, if we look at the deformation of a rubber band, and some materials don't deform easily. So if we have a rubber band and we apply a small force, it stretches, so it deforms. When the force goes away, the deformation also goes away. So in a metal, in a, let's say, a steel rod, the deformation is going to be extremely small, but it will still be there. So let's assume that we take a steel rod or a metal rod or any other material would also do, and we hold it firmly on one side and we pull it with a force F to the right, and if the original length is L initial, due to the application of the force, the rod will become slightly longer. Now this is shown sort of exaggerated. A metal rod would not expand that much. A rubber band, of course, could expand that much. So this change in length is a delta L. So the length would increase slightly. Now if we want to find how much is the delta L, we would see that it's proportional to the force. So the bigger the force, the bigger the stretch. We can also see that delta L is proportional to Li. So if this were longer, suppose it were, let's say, twice as long, if we had a rod that's twice as long and we applied the force here, well, this part would stretch by delta L and the other part would also stretch by a delta L, same amount, and so the total stretch would be 2 delta L. So if it's twice as long, the stretch is twice as much. So that the elongation is proportional to the original length. Now we can also see that if we look at it from the side, then if we have, let's say the rod is like this, it's one of a square cross section. That is this rod seen from the side, and we're pulling it this way, and it stretches by this distance. Okay, so it stretches and becomes, this is the delta L. But if it were a thick rod and we applied the same force, then it would probably pull out just a very little tiny bit. So depending on this area, the stretch would be smaller or larger. So a smaller area would mean a bigger stretch. Therefore the delta L is proportional, inversely proportional to the area. Now if we combine all three together, we could say that delta L is proportional to, let's write the Li, F, and an A. And if we bring the Li on the other side, we can say that delta L over Li is proportional to F over A. This fractional increase in length is called the strain, and the fractional increase in, and the force per unit area is called the stress. So this is written as an epsilon and this is written as a sigma. So we say that the strain is proportional to stress, or the stress is proportional to strain. And we will have a proportionality constant, which is called a elastic modulus. That is the ratio of these two. So the elastic modulus is the stress over strain, and that's F over A divided by delta L over Li. Now there are three kinds of stresses that we will look at, and hence three elastic moduli, and they will have different areas, and they may have different strains. We can't say different delta L by L, but they would have different strains. So the first one that we look at is called the tensile modulus, or the Young's modulus. And that's written with a Y. The Young modulus deals with cases like this, where you pull something and it becomes longer. And this is a tensile modulus and a tensile deformation. So we can say that the Young's modulus Y is F over A over delta L over Li. Or we can also write it as F over A equals Y delta L over Li. Now, if we plot this graph, this would be the y-axis, and this would be on the x-axis, and this would be the slope. So we get a curve like this. This is the strain, and this is the stress, F over A. This is delta L over Li, and because it's a equation of a straight line, we have a straight line here. That's how it would behave. It would be a straight line. So if we keep on increasing the stress, the strain will keep on increasing, and it's a linear relationship. You double the stress, the strain is double. In other words, if you double the force, the elongation will double. Now this continues for a while, after which the curve shifts like this. This part up to here is called the elastic behavior, or the elastic region, and beyond that we have what we call the plastic region. So here the thing, a small increase in the stress makes the strain large, so it starts pulling, and then a point comes where it breaks. Now in this part, if you stretch it from 0 up to say here, and then you release the stress, it will go back to the original length, and then you pull it again to the same force. With the same force, it stretches by the same amount, and then it comes back to the original. And you can keep doing that as many times as you like. It will keep on stretching and keep on coming back. So as an example, which is not exactly correct for a tensile modulus, but it shows the same thing, that if we have a force that tries to pull it, if I pull it and release the force, it goes back to the same position. So because it's so long, it's still in the elastic region. But if I apply a bigger force, then it doesn't go back to the original position. So it has now entered the plastic range, or we have plastic deformation. So this is elastic deformation, this is plastic deformation. An object that's pulled up to here and released, it will go back here. But if we had pulled it up to here and then released, it would have gone back. It would have this much permanent deformation in it. And well, then it could break ultimately. So this is the tensile modulus. And typical values of Y would be some number 10 to the power about 10 newtons per meter square. And that's the unit for the modulus, because the unit for strain is meter per meter, so dimensionless, and this is newtons per square meter, so that's the unit of the modulus.